Our next speaker is Harris Teague. Harris is a principal engineer at Qualcomm AI Research. Recently, he's been focusing on optimizing neural networks for execution on resource-constrained devices. His team has developed methods for model compression and quantization that can be applied to many model types, reducing memory and/or compute required to execute the model on a device. Prior to this, he worked on various different projects, from autonomous drones to UMB. He's the inventor of over 60 US patents and holds an engineering PhD from Stanford University. And today, Harris will tell us about optimizing inference efficiency for tiny DNNs. Thank you.
Thank you. Very happy to be here. I decided today to talk about kind of a broad range of things. We're actually active in a number of different areas, and I won't be able to go into great detail in particular areas, but hopefully this overview will be helpful for you to better understand kind of some of the principal areas that we're working at Qualcomm AI Research. Qualcomm, as you probably know, is fundamentally a mobile company. We think about that a lot, and naturally, because of that, edge computing and edge AI is extremely important for us. And we're seeing more and more AI algorithms, which should be no surprise to this group, operating at the edge and on mobile phones instead of all in the cloud. And this is beneficial for a number of reasons, for latency, privacy, security of your data, et cetera. But it does come with some significant challenges, mainly when resources, in particular power, are limited. For this reason, we make chips that have dedicated capabilities for mobile computing. Here's a few of the areas of specialization, all the way from automotive and drones to IP cameras, extended reality. You get the picture. But we would like for our hardware to be applicable and optimized for all of these important use cases. And so and you can see some of these would be considered edge, and some of them would be more in the realm of tiny, which is what the focus is for this group. Okay. Okay, so let me get into the details. Here are a list of some things. I'll go through these, and I'm going to touch on about half of them in more detail. First, I'm going to say a little bit about optimization, compilers, and schedulers. Actually, if you were here on Tuesday at the tutorials, Jinwan Lee from our team went through in much more detail on this. We also have work in architecture optimization, including architecture search. The next major area is network pruning, factoring, and compression. And then we're working on training mechanisms that are specifically tuned to produce models that are more applicable for tinyML applications. Quantization, which a lot of people have been talking about, we've been doing some research on that, and I'll talk about some angle of that in more detail in this talk. We also are working on specialized digital accelerators, which are tuned to run machine learning type of workloads very efficiently. And finally, if you saw the panel on compute and memory earlier today, I have a little bit of an update on some of the work that we're doing there as well. Okay, first, optimizing compilers and schedulers. So here is a look at some of the type of networks that are kind of emerging a little bit more recently. Rather than your pure linear design, there are some results that show that these kind of networks, when you do a neural architecture search, we're kind of calling them irregularly wired, such as RandWire and SwiftNet, can actually move the Pareto front more to the up and left, which is the desirable direction. But they can come with challenges of scheduling. In particular, these kind of scheduling this kind of graph in a topological sort is exponential complexity. And so how do you kind of solve this problem when you're trying to minimize some parameter, whether it's DDR bandwidth or local memory utilization? So we have a work. If you want to look at the details, this paper, which is coming out in MLSys, there's also an archive version out currently, talks about some of the details. But you can see that with SwiftNet here, with random wire for a couple of different use cases, there can be compelling advantages in this. And this dimension is peak memory, reducing peak memory requirements. And as I'm sure you know, the peak local memory can have a big impact on your latency as well as your power consumption, as it can reduce the amount of times that you need to go out to external memory. So this is an interesting area of research, and we're seeing some benefits there. Okay, so I'm going to move on to network factoring. Essentially, this is the network optimization area. And I wanted to point out some of the methods that we're using in compression. For compression, we have some work focusing on tensor factorization, and spatial SVD is a good example of this. Channel pruning, and we've even built some mechanisms and some algorithms that combine these methods. And here are some results that show how even with, my pointer is not cooperating. Some of the compressions of significant levels down to 2, 3, 4 times. You can, if done carefully, you can maintain accuracy of these models. And here are some ImageNet models which are an example of that. And so you can see that we're preserving accuracy quite well in this ResNet 18 model. Now, we've built general tools that this can apply to lots of different types of network architectures, but here's one result that I wanted to show. Much better, thank you. Okay. All right. Okay, so here's an example of the application of this. We did a pose estimation model. Took one kind of off the shelf. We actually implemented it, but one that was in the literature. And ran this model on some data. Now, the way this is constructed is the models are running purely on these two devices, and the screen behind it is simply giving it something to look at. So the screen behind it is, you could turn this on real images and it would do something similar, but we just wanted something controlled for the demonstration purposes. Well, the compressed version, using the tools that I mentioned before, is on the bottom. The uncompressed version is exactly the same device, exactly the same DSP that's running this. It's just a smaller model and it runs faster. Same 8-bit quantization. So what you can see is this can really make a difference. The one on top, it's reading out the frame rate of about 5.5. Down here, we're getting 20, which is quite an improvement. And importantly, you can see that this kind of improvement makes the difference when you're doing pose estimation on moving subjects, because the lag in the pose estimation is quite apparent in this case. Okay, so I'm just going to train moving forward. I'm going to talk a little bit about quantization here. All right, so quantization can be done in a lot of different ways. I'm just going to describe two key ways. One of them, which a lot of people are familiar with, and we're also working on this, is quantization during the training process. So you build quantization modeling into your training pipeline, and then you can train the model to optimize efficiency, but learn not only what the parameters are, but some of the quantization parameters as well, and we're doing that. This is not that. This is assuming that you have a model and you want to quantize it, and you don't have access to the training data, don't have access to the training pipeline. And in fact, This happens an awful lot. I was actually surprised how often it happens, but generally customers may have either subcontracted their model generation, or they may not have access to the full training set, or you may want to do this kind of quantization and somebody may not want to give you the full training set, which makes that model pretty difficult. Now, of course, you can quantize a model. You can just take all the weights and activations and slam them to 8 bits, and that can work in some cases, but a lot of you may know that that can cause some fairly extreme accuracy degradations for certain use cases and certain models. So what we've come up with is a suite of features that allow you to do this post-training quantization, meaning assuming you have no training data, and it actually can do better than just a brute force quantization method for retaining accuracy. I'm listing a few features here: cross-layer equalization, batch norm folding, high bias absorption, bias correction. These are names that we've given to features, all of which can improve accuracy for this post-training quantization case. And we actually have some papers that go into great detail on this, that if you're interested in the details, you can look at that. So how well does this work? I'm just going to give you a little bit of results. MobileNet v2 results, DeepLab v3 results. Over here on the left is the full floating point accuracy for each of these models. Conventional 8-bit, this was kind of selected to really illustrate the problems of the brute force quantization. So you can see you essentially get nothing out of a conventional 8-bit quantized MobileNet model. And for the DeepLab v3, your results are pretty much unusable with that. Again, I selected models where this was a real problem. And then you can show that with our techniques, these are some of the list of those techniques that I mentioned. And they kind of incrementally give you more and more. You put them all together, and you can do a pretty impressive job of getting back to a level of accuracy that's quite usable. This is pretty. I think this is pretty impressive. This is at the bottom is a citation of a paper that'll talk about these details. A little bit of an early teaser. We have some more techniques that also are very compelling in this same class, but they're in submission right now, and hopefully that'll get accepted, and you can take a look at that as well. Okay, so lastly, I'd like to talk about in-memory computation. Okay, so I borrowed, with permission from Professor Verma, this picture, which I think is useful, saying some of the benefits in these domains where you have energy efficiency versus normalized throughput. Kind of an interesting way to show the graph, but it is representative, and up and to the right is better. And this does show that this in-memory computing techniques have some potential for really pushing the envelope in this direction. He also does point out that in actual implementations, there are still some challenges to scaling this hardware to what you might even consider usable size, certainly for larger use cases and larger models. And folks in hardware are working hard on that. So anyway, this is kind of a motivation why we see this as being compelling. But there's lots of things to look at in this area, and I just wanted to put a list of some of the domains of options for technology choice that we're looking at, just to give an appreciation for the large scope of what your alternatives are if you wanted to pursue this. Process technology, the panel talked a little bit about the manufacturing domains, whether non-volatile memory directions, SRAM and DRAM that we're familiar with. The fabrication capabilities are a big factor for these, especially if you're looking at near-term commercialization versus long-term commercialization. The choice of how you actually want to do the analog mixed signal, whether it's charge or current. There's different bit cell types that you can choose for this. How do you combine the bit cell outputs? Array architectures, because you eventually are going to have to choose how you slice and dice this computed memory tiles. You have sizing and number decisions that are going to have to be made, and And then decisions, I mentioned shared and non-shared. So do you want to try to put lots of tiles and put all of the weights in, or do you want to be shuttling memory in and out of the computed memory tiles as you're computing a model? Naturally, it's going to be some balance of that, but that's a big consideration when you're building these things. How many bits you want to support? Clearly, you can go from binary to multiple bits. In computed memory, it has a big impact. In digital, it does, of course, but particularly in computed memory, where you have analog to digital conversion that is going to be intimately part of your engine, these bit width support has a big impact. Okay, and then analog portions are going to create error sources that are going to be stochastic. Some of them are fully thermal oriented, some of them are more manufacturing and chip sample, and you have to take all those things into consideration. So we have done some analysis in two main use cases, a small VGG type image classification use case and keyword spotting. This is a picture of a network that we've constructed that is for keyword spotting, and it's optimized for computer memory implementation. And you can see it's multiple convolutional layers with a connected layer at the end. This diagram over here is really, I won't go into a whole lot of detail, but it illustrates the problem of mapping bits in an in-memory operation into usable compute rows. And you can see that by nature of convolutions, there's a lot of reuse of activations and weights, and so there's a whole thing you have to manage the complexity of feeding the data through this, and that is another thing that has to be thought through very carefully, or your memory, your power advantages can be easily lost in this kind of detail. Just a little bit of results. We have shown implementations for two of these. The first one here is the image classification, the small VGG on CFAR10, and what you can do with implementation in computed memory with the architecture that I mentioned before. And then we're also working on fine-tuning an architecture where you want to be robust to the types of errors that computed memory introduces. And so you can get some of your performance back. We actually found that for this optimized model here for keyword spotting, we lose quite a bit without fine-tuning after computed memory assumptions, and we can gain back a lot of that. In fact, we actually exceeded the performance of the no-noise case with fine-tuning in a computed memory architecture. And as usual, I think that's just evidence that the original architecture was over-provisioned, and so we may have added some regularization that improved that performance. Now, the big deal here, what is the power profile for these? And you can see that for these three model types that I put here, you can get anywhere between, say, 4 or 5 times TOPS per watt power advantage. And know that TOPS per watt is not necessarily a perfect metric, but it's something that folks are familiar with, and we are seeing some compelling advantages for the computer memory implementation for these types of models. Okay, next steps. This is particular for computed memory. We're expanding our multi-bit design. We are working a lot on hardware and algorithm co-design, which is something that was stressed earlier. And we're working on compiler and scheduler techniques that are going to help us with mapping these new types these types of networks to this type of accelerator that has its own constraints, a little bit different from a full digital accelerator. Okay, and that's what I have. Thank you very much.